Section 8.7. First couple things are absolute and relative error. If you're trying to find an absolute error, one of them, sub C is the computed numerical solution, and X is going to be the exact solution, so the absolute error would be the absolute value of C minus X. So C being the answer you got and X being the real answer. And then the relative error, is exactly the same thing, except you're dividing by the actual answer, as long as it's not 0, which is going to give you a percent written as a decimal. So for example 1, when it says, the ancient Greek used 22/7 to approximate the value of pi, determine the absolute and the relative error of this approximation to pi. Okay, so absolute error is going to be 22/7 minus pi. If you put that in your calculator, and your calculator is using many decimals for pi, you get 0.00126 is the absolute error. The relative error, all I've got to do is take that answer and divide it by the real answer, your absolute error divided by your exact answer, and you get 0.000402, which if I make it into a decimal is 0.04% error. So the Greek's approximation is really, really close. The next thing we're going to do is we're going to try to figure the area under a curve by drawing little rectangles. This is known as Riemann sums. You actually can do left endpoint and right endpoint, where your rectangles touch on the left corner of the rectangle or on the right corner of the rectangle where they touch the curve. But the midpoint would be more accurate. And so what you're doing is the area of a rectangle is length times width. So the area of one rectangle would be length times width, and you want to add them all up. So the formula becomes the midpoint approximation, and we're going to call it midpoint approximation for the area under the curve, which would be the integral sign we've been using, of f of x dx. So we're kind of going backwards now. We know how to do an integral, we know how to get an exact answer, but now they want us to see how you do it numerically, how it was done before they discovered how to integrate. And so what you do is you are summing up k equals 1 to n being the number of rectangles involved, the function evaluated at one point and the point in front of it. So x sub k minus 1, you're finding the middle between two sections all over 2. That would be a midpoint. And timesing it by the thickness of a rectangle. So what's happening is, if you take a curve and you're going from A to B, you would chop it into equal pieces, pretend those are equal, and you would draw in rectangles at the middle of the rectangle. So what should happen is the piece that you're too big on right there and the piece that is an underestimate will balance each other out, and you'll get a fairly accurate area. So to find that middle spot, this spot right here, you would take this one, x sub k, and the one that's before it, x sub k minus 1, add them together, divide by 2. That would give you the middle point. And you plug that into your function, so this would give you the height of the rectangle. This piece is the height of the rectangle, and delta x would be the width of the rectangle. And delta x is figured by taking b minus a, so the distance that you're doing your integral on, divided by the number of rectangles you made. And so what happens is you are taking the length times the width, or the height times the width of the rectangle, so this whole piece would be the area of one rectangle. And then you do the summation, so you're going to add up from 1 to n all the rectangles. So let's look at example 2. Wants us to approximate the integral from 2 to 4 of x squared dx. Using the midpoint rule, they want us to have 4 rectangles. They also want us to do it again with 8 rectangles. Okay, so first with 4. With 4 rectangles, I would be starting at 2. First point, not a sub 1, a, is 2. The next spot would be from 2 to 4, let's figure that out. Delta x is going to be equal to 4 minus 2 over 4 rectangles, so each rectangle is going to be a half. So this one would be at 2.5. The next one would be at 3. The next one would be, oops, I'm running into myself, 3.5, and then x sub 4 would be at 4. So we really call this A1, this first one here, we call it x sub 0. And the last one was your your B. So now I need the middles of all of them. So what's the middle between 2 and 2.5? 2.25. The middle between the next two would be 2.75. The next one's middle would be between 3 and 3.5 be 3.25. And the middle of the next rectangle would be 3.75. So I have all of my middles. Now, in order to find the midpoint of 4 rectangles, that's how they're going to designate it, they're going to do f of the first one times by how thick it is, plus f of the second one times by how thick it is, and so on, the third one, and the fourth one. So what am I actually doing? I could make this easier in my brain, and I could write it as f of, well, let's see. If I plug in m sub 1, it's going to be, can I pull a delta x out? That make it easier. I'm going to go like this. Not quite sure I like the way the book wrote it. And I'm going to take delta x out. So all I got to do is plug them in. So I'm working with 2.25, plugging it in the original equation, which is x squared, so 2.25 squared, plus the next point is 2.75 squared, and then 3.25 squared, and then 3.75 squared, and the whole thing is multiplied by how thick is one rectangle? 0.5. When you do that, you get 18.625. So the exact area of this, they're telling me, we could integrate this and get the exact area, and the exact area is 56 over 3. So if I'm trying to find the absolute error, I would get 18.625 minus 56 over 3. That's supposed to be a 6. And the book says approximately 0.00223. No, wrong one. 0.0417. Sorry about that. And then if I want to find the relative error, I get that 0.0417 and divided by the 56 over 3. So we have 8.625 minus 56 over 3 all over 56 over 3. And we get 0.002223, which is approximately 0.223% error. Then if we do it again with 8, and I'm not going to, but if I want 8 intervals, I would have to redo this with my delta x being 4 minus 2 over 8, so 1/4, and that would give me 8 rectangles. So I'm summing up all 8 of them. the summation of all 8 from k equals 1 to 8, oh, not infinity, 8 of all the midpoints times by the thickness of the rectangle. They say if I do all this out, I get 18.65625. That error, the absolute error is 0.0104. Absolute 0.0104. Relative 0.0558%. So you see, if you take more rectangles, you're going to have a smaller error. Now that's how you do the midpoint.